Hi, we present vMAP, Vectorized Object Mapping for Neural Field SLAM. vMAP is an object-level dense SLAM system using neural field repetitions. Each object is replicated by a small MLP, enabling efficient dense object modeling without the need for 3D pliers. Given a real-time RGBD input stream, vMAP detects object instances on the fly and dynamically adds them to its map. Thanks to the power of vectorized training, vMAP can optimize as many as 50 individual objects simultaneously in a single scene, with an extremely efficient training speed of 5 Hz map update. Each object can be individually controlled, edited, and further recomposed together into a scene-level repetitions. IMAP is the first real-time neural field SLAM, showing a simple 4-layer MLP can replicate a whole 3D scene. And the next SLAM further combines hierarchical feature grids with MLP decoder, able to reconstruct larger scenes. Both of them show the map surface will be more continuous with plausible hole filling compared to TSDF-based depth fusion method. However, the correspondences between network parameters and specific scene regions are complicated and difficult to determine. Recent decomposed NeRFs usually split the 3D scene into small grids, and each 3D grid is replicated by a small network. KiloNeRF further shows that multiple tiny MLPs can speed up NeRF training than directly optimizing a single large MLP. Those decomposed NeRFs can model each part independently, however, they are not semantically meaningful. Some method fuse semantic features into neural field and can query semantics via click or language. Object NeRF replicates each object as a latent code and simultaneously train all object codes and MLP decoder. However, those methods either cannot achieve real-time mapping performance or cannot incrementally take new semantic objects under SLAM settings. Therefore, we want to build a real-time object-level neural mapping system with object-level representation, composable map, implicit 3D representation, and efficient real-time performance that can manage objects parallelly and flexibly. Specifically, we have depth-guided training that efficiently focuses more on the object surface. By applying depth-guided resampling, additional depth supervision, and surface volume rendering, the geometry quality and converging speed is obviously improved. To obtain object-level representation, we have object association by checking semantic and spatial consistency. For supervising each object model, we have occlusion-aware sampling based on 2D mask and depth measurement. We will early stop rays to avoid damaging target object while able to clean the occlude part. We can obtain plausible object-level completion without any object shape pliers. The vectorized batch model training is implemented at Python package level using FuncTorch, without the need of customized CUDA kernel. Here we show a high-level code demo. Multiple networks batch training can be achieved by simply 4 steps. Firstly, init the batch of models with the exact same structure. Then, prepare the batch training data for the batch models. By just one go inference, we can get the batch of predictions from the network. Next, we can compute the loss of batch models and simply do the backpropagation. Finally, as the batch model is a deep copy of original models, we need to update the network weights to the original models manually. We show that vectorized operation allows extremely fast training speed compared to standard sequential operations using for loops. And we found only 4-layer 16 hidden size MLP is sufficient for modeling a single object, indicating object-level representation is highly compressible. We show camera tracking and real-time mapping results on TUM RGBD dataset. The camera tracking and mapping reconstruction quality is highly interdependent. Thus, we adopt OpenSLAM in our system for cleaner implementation, faster training speed, and higher tracking quality. For 2D metrics, we evaluate novel view rendering. For each replica scene, we randomly generate a new trajectory, compared the rendering views to the ground truth view. We find vMAP can get much clearer rendering, especially for foreground objects. For 3D metrics, we evaluate at both scene level and object level. As we found, the scene level metrics are dominated by the background meshes, while object level metrics are averaged across all the objects, letting each object contribute equally. Another motivation is in robotics, like navigation and manipulation, objects are normally more important than the background. We also compared object-level performance against classic TSDF fusion and Object SDF on real-world dataset ScanNet. Object SDF is trained offline without depth info, while vMAP is online mapping with the help of depths. We show vMAP result on real-world data. For ScanNet, as we can see, the object mask and depths are noisy. And for our own recording with Kinect, we use off-the-shelf object detection frontend, DETIC, and adopt real-time camera pose estimation from OpsLamp 3. vMAP can get more complete reconstruction of multiple objects in real time. Please visit our website for more information. Thanks for listening.